Hi everyone, this is Yuke, and today I would like to introduce our work empowering the multi-GPU deep reinforcement learning with adaptive grand parallelism. With that, let's start with some background of the deep reinforcement learning. It covers a wide range of applications, like the autonomous driving, and also industry for robotics, and also many other power grid control. Those are a wide range of applications. And with these kind of applications, let me briefly introduce some of the background for the deep reinforcement learning. We'll start some deep reinforcement learning basics and some of the existing work on the GPU-based deep reinforcement learning, and also how could we optimize its performance based on the GPU spatial multiplexing. Let's start with the basics. For example, over here, it just shows a basic flow of this kind of DRL computation. Let's start from the left. For example, over here, we have the environmental simulation. Basically, try to mimic what really happens in the real-world situation. For example, it could be the robotic arm that is used in the industry for manufacturing. And there is an agent. Agent means it could be real people, or it could be robotics that interact with this kind of environments. And for each of the agent, they have two processes. Basically, they want to interact with this kind of environment through prediction, which means what kind of action it will take. And also, it will gradually improve itself based on what kind of experience it has. We call it the training. Therefore, we have the policy training on the right-hand side. And to accelerate this kind of process, there are a wide branch of the optimization has been enforced. For example, over here, we could have used our GPU-based DRL. For example, NVIDIA proposed the SXGen. It could use to train the robotics arm. For example, over here, it try to learn some gestures. And also it could be in the manufacture process in the industry, and also many others. And let's dive deeper into what kind of happens behind. For example, when we abstract this kind of process, it consists of the single state that has the environment to represent the environmental situation, and also one actions to interact with kind of the state. But when we have more of this kind of interactions, we could have many, even thousands of this kind of process happen concurrently. Therefore, we try to parallelism to improve their efficiency. Based on these kind of paradigms, we want to ask what kind of key observation we can have from this kind of interaction process. Specifically, based on our profiling, what we observe is that the overall simulation process, for example, the overall training to improve their policy efficiency, is that they exhibit a cyclic GPU utilization patterns, where those phases actually happened in a cyclic way. And typically, there is a spike, and also there is a lower utilization phases. And further, when we take a look at each of these kind of phases, what we find is that even though there are three phases, and different phases actually exhibit different performance, when we try to extract them and to profile its performance, what we observe is that the simulation actually take a majority of the latency, which means the simulation is the key bottleneck. The second part of the observation is that once we have this kind of a simulation as a bottleneck, what we can do is that can we actually improve its batch size or its concurrency to overcome this kind of performance challenges. Therefore, we come up with the idea that can we increase the number of environments in order to tackle this kind of efficiency issue. But our answer is that based on this kind of graph, this figure, what we have is that the larger simulation batch actually hardly work in this kind of situation, which is quite different from what we have from our deep neural network training or even the large language model training to increase in the batch. And furthermore, when we test out this kind of GPU utilization versus the number of environments, what we also observe is that even we increase the number of the size of a batch, the GPU utilization could still be low because of the simulation, they could not easily scale up as we typically scale the deep learning training or inferences. Therefore, our idea is that instead of letting this kind of algorithm to fit what we needed, can we do it in a reverse way? We let the hardware to fit what kind of computation demands we have. Therefore, we try to look at two major solutions. One is called the NVIDIA MPS, and also another is more at a hardware level, the MIG. But the key here is that we tailor hardware resources to fit the computation. While this sounds very straightforward, but there is some challenges. For example, over here, when we have different kind of GPU in terms of their different sizes, the first thing we want to determine is that what the number of the instances. For example, the number of the instances we want to put in on each GPUs. So this is one of the granularity issues. The second part is that once we decide what is the size or what number of the instances put into each of the GPUs, the second thing is that what kind of interconnect between this kind of instance, either within the GPU or among different kind of GPUs. Therefore, how to connect the connection is another major issue. Based on this kind of observations, we want to highlight our designs. Firstly, we want to introduce our process-based programming to bridging users and all these kind of instances. The second is the adaptive management, which basically how could we handle the granularity issue. And thirdly is, as we suggested, is the communication issues. How do we effectively connect among different kind of instances and also GPUs? And this is the overall picture from our designs. And we will dive deeper into each individual components and to demonstrate what happened behind. So let's start with the process-based programming. This is a high-level user interface that we expose to the users to highlight what kind of method we want to provide. So starting with this kind of coding examples, over here, we highlighted the basic function that we want to implement for this kind of programming paradigms. We cover the simulators. This kind of method we typically want to implement is that how could we send and receive the information, which means we gather the information and also generate the states. And the second part is that how could we interact with the simulators, including how could we either communicate with among agent and also interact with the simulators. And finally, for the trainers, the communication pattern could be even more diverse, including how we handle the collective communications. And the second part, major part, is called how could we control the granularity, because granularity, as we just suggested, is one of another issue. Specifically, we want to because we want hardware to fit what kind of computation we have, we need to have a resource-aware instance mapping. So over here, the key is that how could we map each of the instances, which is each of the training instances, to the GPUs. The second part is how could we manage the communication among different kind of instances. And the second part is that once we have this kind of mappings, what kind of workload we need to use in order to fit this kind of instance layout. So here is that how could we make the instances more resource aware and also to maximize out their runtime efficiency. Let's begin with the resource-aware mapping. So essentially, there are several typical paradigms. The first one is a most straightforward one, but it can also functionally well in a different kind of situation, where we have all this kind of three different phases co-located on the same instances, such that we just follow a very fine-grained data parallelism. The second part is decomposed, parallelism with both the data parallelism and also the different phases separated on the different GPUs. For example, over here, we lay out the trainers together on different GPUs, while put the serving phases, which we try to collect the different kind of experience on another GPU instances. But the key question here is that how many of this kind of serving or training instances should be placed on each of the GPUs. So our current solution is that we can perform a workload-aware instance selections. Here's the overall algorithms, but we want to highlight what kind of case step we have been performed in this kind of process. So firstly, we want to get to know what kind of the computation or what kind of resources is actually can actually fit or not fit in this kind of instances and workload matching process. Essentially, we want to accommodate different kind of the workload, as well as we consider what kind of performance we can get. And the second phase is once we've done this kind of search, in what kind of step we need to stop. For example, we have a search through all the entire spaces. We want to know at which phases we want to we already collect sufficient useful runtime statistics such that we can actually early exit at this moment. So the overall process is just a two-step. One is to perform the profiling. The second is that to stop at the right place. Once we have done this kind of like workload versus like instance matching process, the second part is that how could we effectively handle the communication? Because all these kind of instances currently are just standalone. Therefore, we have our hierarchical gradient reductions, and also the latency like to connect different kind of instances. And furthermore, for the asynchronous process, we will also have the channel-based experience sharing. And basically, we want to improve this throughput in these kind of situations. For hierarchical gradient reductions, what we have is that we have several different kind of patterns. This first one just to try to connect all the instances together, regardless of where the instance is located at, whether within the GPU or across the GPU. The second part is that can we connect them with efficient connections, like the NVLinks, by grouping them across different rings. The third part is that try to hybrid those two together with different parameters. And essentially, we try to parallelize the intra-GPU reduction and also minimize the inter-GPU traffic. And the second part is for channel-based experience sharing, where we try to handle when we have a large batch of the experience, how could we effectively move this kind of experience from one GPU to another? So the key question here, our key paradigm here is that how could we effectively do the data movement? So the first phase consists of how could we effectively dispatch. The dispatch means once we have this kind of large tensors or large number of the experiences collected by the serving process for the deep learning learnings, how could we break them down and also group them together? Because for different kind of data tensors, they have different shapes. But how could we lay out this kind of different shapes, align them together, such that we can maximize out the data movement performance? The second part is that once we've done the dispatching, and also the packing part, as we suggested, is that for different granularity, for example, small data tensors, probably they need more number of the small data tensors to group them together into a larger tensor to movement, while the larger tensors just move them as in a smaller number. Or we can hybrid both. And furthermore, this is a migrated process. And lastly, we just put them on the trainer to do the computation. But there, actually, we skip to show one of the processes that we somehow need to decompose the packed data type. So let's take a look at the experiments. So essentially here is that we've done a bunch of experimental testing. Over here, we have different benchmarks across different domains, and also the networks on the different policy on the policy trainers. And the platform we choose is the DGX A100 with NVLink, and those are the libraries we used, including the NVIDIA ISAC and also PyTorch framework for training, and also the Nico for communication, and Honevoid for scaling across different kind of platforms. And for performance-wise, what we observe is that we typically we compare with one of the ISAC for serving. For example, the policy serving is one of the way to connect the different kind of the experience. So over here, what we have is that compared to those kind of coarse-grained serving, where one of the simulator or the actor try to occupy the entire GPU spaces, we have achieved 2 point or higher throughput on average. And for the second part is that for training, we try to compare with the framework that directly scaled with the Nico libraries, which means this is usually the common practices in this domain to try to scale up the GPU or try to scale up the performance with this kind of collective communication libraries. And here we also harvest more a throughput on average compared to direct scaling. And furthermore, we also compare with a platform for different kind of platform which integrated with the Honevoid in terms of their communication performance. What we found is that our throughput is still achieve relevant advantages. The lastly is just a short comparison among different kind of techniques we used for instances. For example, over here we have MPS and MIG in the service. What I observed that for this kind of service situations, the MIG actually performs better because of their more low level isolation for resources, such that they can avoid more interactions or more interruptions among different kind of instances. But for the communication required settings, for example, the policy trainings, probably in that kind of situations, the MPS would perform better because they can lower the cost of data movements among different instances. We also compare with the array in terms of the RL lib inside their libraries for performance. And additionally, the Manspore will also be one of baseline, but more results can be checked on our paper. And thank you. And our work will also be open sourced. And if you have any questions, just feel free to let us know. And our work consists both of the code for how could we do transfer at the front end, and also the back end for the evaluation. Okay, thank you.